All right, guys, I'm going to finish up section 17.6. We got through most of it, but we have some stuff to finish up at the end. So let's go through that. I finished lecture discussing orientable surfaces and their normal vectors. So I'm going to quickly go over that again just because it has a lot to do with the surface integrals that we're going to calculate below. So let me just remind you. Okay. So yeah, so our final task in this section, we've learned how to integrate a scalar function over a surface. We did that above, but we haven't talked about how to integrate a vector field over a surface. It turns out that we have to be a little bit careful with the types of surfaces that we integrate over. They have to be orientable surfaces. Basically, what this means is that they have two sides. It means that the normal vector varies continuously over the whole surface. You can't walk along the thing and then get back to the same point and your normal vector is pointing the other direction. So this is kind of surprising, but yeah, some surfaces are not two-sided, which is kind of a strange concept. I think I showed you this in class. These two are orientable. If you think about a sphere or like maybe this kind of umbrella shaped thing over here, those surfaces are both orientable because they have two sides. This is an easy one to tell. You can see you could walk along the underside of this or the top side. It's like a piece of paper, it's clearly got two sides. This is an open surface. This one over here is a closed surface, so it's the analog of a closed curve. However, it's still two-sided. You can imagine if you're an ant maybe walking along on the outside, you're going to stay on that side. Whereas if you were inside, you'd be walking up the wall and inside circling around. So that would be the other side of this surface, but there's clearly two sides. All right, but not all surfaces are orientable, which means that some surfaces have only one side. So here's an example of one. I showed you one of these in class. This is called a Mobius strip. And what it is, if you take a rectangle, put a half twist in it and glue the ends together, you end up getting this shape which has only one side. So, if you were walking on it locally, you might think that there's two sides because, you're on the opposite. If you were to look underneath it, you'd be like, that's got to be a different side. But if you were to walk along this thing, what you'd notice is that you'd end up on the other side without crossing any edges, which means you're really on the same side. All right, so we're not going to be calculating surface integrals over these types of surfaces. By the way, there's a four-dimensional version of it. Basically, what you do is you take two Mobius bands and you glue their edges together and you get this shape. It doesn't exist in R3. It exists in R4, so we can't exactly visualize it. It's called a Klein bottle. We can look at its projection in three-dimensional space, but the actual Klein bottle lives in four dimensions. But this would be the projection, just so we can get an idea of kind of what they look like. This would be a projection in three-dimensional space. But this thing only has one side as well. You can kind of see the idea of what's happening here. If you walk along this surface, and you kind of have to imagine that this intersection is not there. If you can imagine it's not there. If you were to walk along the surface as an ant, you'd be on the inside and the outside, and the inside is the outside. So we're not going to be working with those, let alone surface integrals in R4 anyway, but I just thought I'd show you that because that's a real famous mathematical shape. All right, so let's say you do have a surface that's orientable. So how do we orient it? What do we do? What does that mean to orient a surface? Well, if the surface is orientable, essentially that means that there's two normal directions. So for example, this closed surface here, if you look at a point on the surface, there's going to be one direction that points directly straight outwards, kind of normal to the tangent plane. And there's going to be another vector that points directly straight inward, which is also normal to the tangent plane. There's two of them. So, one of those, well, we're both normal, but we can pick one of them basically, which will orient our surface. So You know, if the surface is closed like this, you always pick the outward vector to be the normal direction, like so. So it's pretty straightforward if you have a closed surface. You don't really have a choice. I suppose someone could orient it so it points inward, but they would have to tell you that specifically. You should assume that normal vectors for closed surfaces always point outward. But the question is, what if the surface is not closed, right? Like these guys. So like both of these surfaces, essentially the same surface, they're not closed. So what do you do in this case? Well, you kind of have the freedom to choose whichever direction you define to be the normal direction. Okay, so for example, in this one, we're defining the normal direction to kind of point in the upward direction. And in this one, we're defining the normal vector to point in the downward direction. So you kind of have a choice here. Okay, now when we get to Stokes' theorem, you're going to find that your choice has to be consistent with something else. So you don't have a choice there, but in general, you do. You have a choice. All right, so let's see. You guys remember how to parameterize a surface? And let's see, did we find TU? Yeah, we found TU cross TV, so we know how to do that. And by the way, that vector right there is normal to the surface, right? So it's going to point in one of those two directions, just so you know. Okay, so if it doesn't point in this direction, it's going to point in that direction. So that means either your normal direction is going to point in this direction, or it's going to point in the negative direction. Those are both vectors, right? Okay. All right. So let's see. When evaluating a surface integral, we're going to have to choose how to orient the surface. Okay, so we'll see that in examples 7, 8, and 9. All right, so finally, let's evaluate some surface integral of a vector field. Maybe I'll change this around. Oops, need to fix something. We call a surface integral of a vector field. We call it a flux integral. So I'll just write flux or surface. Put it over there. Sometimes we'll just say find the flux, but it means a surface integral of a vector field. And we're going to do it once for a parametrically defined surface, and then I'm going to show you how to do it for an explicitly defined surface, just like we did for scalar surface integrals above. Okay, so let's do the parametrically defined one. Kind of go through the argument here. So first of all, what does it mean to find a surface integral of a vector field across a parametrically defined surface? Well, you know, when you think of a vector field, you know, we're kind of picturing it as a bunch of arrows, but you can kind of think of it like a flow of some substance, right? Or a movement or a transport. So maybe that substance is water, maybe it's air, maybe it's a river, maybe it's birds migrating around, maybe it's the transport of guns moving into a country. It's just a flow of a substance. So with this interpretation of a vector field, it makes it a little easier to understand what a surface integral of a vector field is. Basically what it is, it answers this question. How much of a substance, whether it's water, birds, guns, whatever, passes through a given surface? That's what the surface integral of a vector field is. And we refer to this as flux. It's how much passes through, so it's flux. So let's develop the surface integral, and you'll kind of see this is why you'll kind of see how it answers this question. So let's start off with, let's say we got a continuous vector field, and let's say we have a smooth surface S, kind of like this one over here. This is its parameter region over here, and this is its parametrization. And let's say, yeah, we have a rectangular region R. It doesn't have to be rectangular, but for our purposes, makes our work a little bit easier. Okay, so couple things. The orientation of your surface, you know, you have to pick a direction. Does it point upward or downward? Well, that brown vector right there is indicating that we've kind of chosen the normal direction to be upward. It doesn't have to be, But in this case, we're going to define the upward direction to be normal. And then this red vector right here is representing the vector field restricted to that particular point on the surface. So if you wanted to see, the vector field on the whole surface, that's what it would look like. It's just a lot of stuff. And of course, if you wanted to see the vector field everywhere in R3, it would get even messier. But for now, let's just look at the vector field at one point so you can get an idea of what's happening. So what is happening here? Well, look, if we take a little small little region S, a little small little patch, and maybe we label some point P on the surface, that would be that point. I don't know if you can see it there, right at the base of those vectors. The flux, or the amount of the substance that passes through that vector field, the surface, is proportional to the component of the vector field, F, in the normal direction that we've chosen. All right, and the normal direction is given by that vector N. That's the brown vector right there. So if theta is the angle between F and N, so the red vector and the brown vector, then the component of F in the N direction is given by the dot product of the two. And we know this because by definition, F dot N is the magnitude of F, magnitude of N, cosine theta, but N's a unit normal vector, so we can get rid of that. And then we just have the magnitude of F cosine theta, which is the component of F in the normal direction. All right, it's just a kind of basic trigonometry. Okay, so essentially what we're going to do is we're going to take all of these components of F in the normal direction, which we could write this way, right? And we're going to just add them all up across the whole surface. So that's what an integral is, right? It's just adding up a bunch of things. So since we're adding it up over the surface, we'll use a surface integral. So you write the two snakes and you write an S, it's supposed to be underneath, but close enough. And then we're adding up all of these normal components of the vector field over that surface. And that's essentially what a surface integral of a vector field over a surface is, also known as flux. Okay. So once again, if you kind of think about the different situations you could have here with the brown vector and the red vector, the angle can be between 0 and 180 degrees or 0 and pi, right? So you might want to just first kind of ask yourself, well, what angles would have positive contribution to the flux and what angles would have negative contributions to the flux and what angles would have no contribution? Well, if F and N kind of point in the same direction, let's say exactly the same, that would be theta equals 0, then what happens is F dot N would equal the magnitude of F. Cosine of 0 is 1. So this would be a positive number, and that's a positive contribution of the flux. So this would indicate that all of F flows across the surface in that point in the normal direction, giving us a positive contribution at that single point. And if F and N point in opposite directions, well, that would mean theta equals pi. So if you plug pi in, you get the dot product is negative the magnitude of F. That's a negative contribution to the flux. This would indicate that all of the vector field flows across in the exact opposite to the normal direction that you've defined. If F and N, if they're at 90 degrees to each other, angle of pi over 2, then what will happen here is the cosine of pi over 2 is 0, and the dot product would just be 0. So you basically have no contribution to the flux, and this would indicate that none of F flows across the surface in either direction. Okay, so that's the idea. Of course, most of the angles are going to be between 0 and pi over 2. So these are kind of the edge cases, but it is important to kind of take note of these three kind of edge cases here. All right, so now you remember this. For any parameterization of a surface, we did this when we were doing scalar integrals above. We created this vector Tu cross TV, and we used it to, when you take the magnitude, you get the area of that parallelogram, which estimates the area of the kth patch. But if you actually just look at that vector itself without the magnitude on it, the cross product of those two vectors gives you a normal vector, and that's going to be normal to the surface. right? Those two vectors lie in the tangent plane. So this vector here would be normal to the surface. So what we'll do is we'll take this vector and we'll normalize it. We'll divide by its length, and that'll give us our what do you call it? Unit normal vector, right? Now it may or may not point in the direction that we had chosen for our orientation. So we'll talk about that in a minute. You might have to reverse the orientation on it, but that's easy. Just throw a negative in. But first, let's just go ahead and assume that they're pointing, that your chosen orientation and this vector n point in the same direction. Well, if we appeal to what we did earlier with the scalar surface integral, how do you calculate those? Well, you take your scalar function. In this case, our scalar function is f dot n, right? That's what we're adding up. And then remember what you do is you integrate over the parameter region and you throw in this magnitude of tu cross tv. But we know what n is. So we could throw that in like so. And amazingly, what ends up happening is you can actually cancel the magnitudes of those cross products. And then what you're left with is this kind of simpler form for the flux. Okay, so that's essentially our formula. Now, if you've chosen n in the same direction as tu cross tv, then there's really nothing to do. You could evaluate this flux integral and you're done. But if you had chosen n in the opposite direction, instead of using this, you just want to use the negative of it. Okay. All right. So that kind of summarizes everything in here. This is a summary of everything I talked about above. This is kind of the setup for evaluating these surface integrals of vector fields over parametrically defined surfaces. Let's say we wanted to do this over explicitly defined surfaces, because that's pretty common, right? We don't always give surfaces parametrically. Sometimes they're given, explicitly, like, maybe something like that. It's a plane. It's not given parametrically. So how would we do this? We don't want to have to convert everything to their parametric equivalent. So there's a quick way to handle this. So if S is given explicitly, like so, function of x and y, we already know that a normal vector to the surface is given by this. We kind of prove this up above. So what happens here in this case is that the integrand of the surface integral becomes, oh, I should have put that here. There we go. Becomes that guy. And then everything else kind of follows. We just use what we learned above and plug everything in. So there's your flux integral. And so there's your F, your three-dimensional vector field. And as I was saying earlier, this is tu cross tv, in this case, tx cross ty, which is this guy. So we just, plug that in. Okay. So, and this is assuming that the normal vector is consistent with the normal vector n is consistent with the orientation, or I should say this vector. Yeah, the normal vector, yeah. If it's not, all you got to do is negate it, right? Just negate it and use this instead here. Okay, so it's one or the other. You just have to make sure that everything's consistent there. All right. Okay. By the way, sometimes you'll see flux integrals kind of represented this way. Hopefully you can see why. This is F, let's see, F, G, H. And this is negative ZX, negative ZY, and 1. So when you take their dot product, sometimes you'll see these integrals represented in kind of a differential form like that. Okay. All right. So let's do a couple. So let's say that we've got a vector field. This is a very boring vector field. It's a vector field in R3, and all of these vectors everywhere in R3, they have no x and y component. They're pointing straight down with a length of 1 in the downward direction. Okay, so we're going to be looking at this vector field on this surface S, which is a plane in the first octant. So you get this kind of section. Let's get rid of that. Let's get rid of that. There we go. That's the surface we're going to be integrating over. And the question is asking us to find the flux in the downward direction. Essentially what they're doing is they're telling us how to orient the surface. If they tell you find the flux in the downward direction, that means that the normal direction is downward. Okay, so you don't have a choice there. They're telling you how to do it. All right, so what's going to happen here? Well, here's the idea. You've got your vector field. We're only interested in the part of the vector field that's on the surface. And then we have the normal direction to the surface. It's a bunch of, I was showing you one vector above, but really it's that direction kind of downward. And we're basically going to dot all these guys together with those guys and sum them all up, basically. And when we do that, that's the surface integral of the vector field over that surface. Now, because this is given explicitly, we're going to use that kind of alternate formula that I just showed you. So, we're going to integrate, using that explicit theorem that I just showed you. Okay. All right. So what do we need for that explicit formula? Well, you need Zx and Zy, right? And if you find those and you plug them into our formula which is negative Zx, negative Zy1, you'll end up getting 2, 1, 1. Now, what you have to do is make sure that this points in the right direction. They told us downward flux, right? They said the downward direction is the positive direction. So you have to ask yourself if this points in the downward direction. Downward is Z component, right? So if you look at the Z component, it's positive. So it's not actually pointing in the correct direction. But it's a real quick fix. There's two vectors normal, just negate this one. And then you'll have a vector normal to the surface that points in the correct direction. Okay, that's essentially that TU cross TV thing, right? Just negated. All right, so that's what we're going to use for our normal vector. And let's see. Okay, so we'll take our vector field. It's a very boring vector field right there. And we'll dot it with our vector normal. And we'll integrate over the region R. Now, what's the region R? Well, this is a region underneath the surface in the floor. That's this region down here. Okay, so all we got to do, find that region. You guys have spent some time doing that. It's just a triangle, let's see, in the XY plane with these vertices. When you work out this integrand here, it ends up being 1, which is super nice, because when you integrate the double integral of the one function over a region, what you really just get is the area of the region. So if you can find the area of this triangle without calculus, go ahead and do it. It's pretty easy, right? 1/2 base times height. So you can do that, and you can avoid some integral work. It's easy either way, but so we'll end up getting 4. All right, let's interpret. What is this 4 saying? Well, first of all, the 4 is positive, so that's indicating that the flux is positive. That means we've got a net positive contribution in the normal direction, which is downward. And that seems reasonable because the downward direction was the normal direction, and the entire vector field is, at least partially agreeing with the normal direction. So there's nothing to even fight back against this one. It's definitely going to have a positive flux here. Okay, let's skip over that. All right, let's try another. Let's try the flux of a radial field over a sphere. So this would be a basic radial field, XYZ. Remember, this field it's an explosion radial vector field. It explodes outward at all points. We're only interested on the surface given by this hemisphere. That's a sphere, and that would be the top half of the sphere. So that's a hemisphere. And we want to find the upward flux of F across this hemisphere. And I'm actually showing you the vector field on the hemisphere, just the part of the vector field I care about. And we'll find the flux. And look, they're telling us they're defining the upward direction to be the normal direction. So the first thing you might want to ask is, do you think our answer is going to be positive or negative? Right? If the normal vector is pointing upward, let's see if I can do this. Oh, maybe I need to turn this on. Close that. See if that works. No, it doesn't want it. Oh, okay, not sure why, but the normal vector is pointing upwards, and you can see that all of these vectors are agreeing with the upward or outward direction. I could say outward too, but that's fine. Okay. All right. So we're expecting a positive answer here. So let's go ahead and let's see. This surface is given explicitly. So there's no point in parameterizing it. We can just use that second formula. So you got to find Zx and Zy. Now, finding Zx and Zy, one way would be to solve for Z and then find it. That's going to get ugly. So you might as well use implicit differentiation, right? Just take your equation, differentiate both sides with respect to X, and then solve for Zx. So there's Zx. You can do the same thing for Zy. So this is your formula for a normal vector. So you just plug in your Zx and Zy. And now you've got a normal vector. Now you have to make sure it points in the right direction. Either it does point in the right direction or it points in the exact opposite direction. So what you want to do is just make sure this does. And since we've defined the upward direction, that's positive Z, to be the normal direction, then and notice one's positive, so this is definitely the correct one. We don't need to fix it or negate anything. Okay, so let's calculate the upward flux across the surface S. So there's your flux integral. We'll just plug everything in, plug in your function, your vector field there, plug in your negative Zx, negative Zy1 there. Your vector field is the radial vector field XYZ. Then we'll dot it with X over Z, Y over Z1. And when you dot it, you end up getting this guy. Now, here's the thing. We're going to be integrating over the region R, which is in the floor. And the region R in the floor should only have X and Y values, right? You're integrating the X and Y direction. So we got to get rid of these Z's somehow. There's probably different ways to do this, but here's one of them. X squared plus Y squared plus Z squared, we know that's equal to 1. So that greatly simplifies things. Okay, but we still got the Z there. So how can we rewrite Z in terms of X and Y? Well, you could take this equation and you could solve for Z to express it this way. So now you've got a function of X and Y. All right, now the region in the floor. Clearly, the region in the floor is a disk. So that's kind of pushing us towards polar. And this guy right here is making me think polar. So let's switch to polar. Put that right here. Convert to polar. And I'll let you guys work through the specifics, but I do want to point out that we do get a positive answer. We get a positive flux. Okay, so this is basically a measure of how much substance passes through that surface per unit time, just so you know. 2 pi. All right, we were expecting it to be positive. All right. Okay. By the way, I mentioned this in class, but you've got this table down here for, it gives you parametric descriptions for cylinders, cones, and spheres. Gives you the parameter regions for those. And also, we've done a few of these. We've calculated, a normal vector, TU cross TV, and the magnitude of the normal vector. You need these for scalar surface integrals. You need these for vector field surface integrals or flux integrals. So, you can just use the table. And also their corresponding explicit descriptions are here with their domains. And there's a normal vector, and there's the magnitudes of the normal vector. So keep in mind, you might have to reverse the orientation, here, depending on the setup of the problem. All right, let's do one more. How about this one? Okay, so this is interesting. We're going to basically, it's a similar problem. We got the same radial vector field, and we're going to calculate the upward flux of the field across this paraboloid. And we're going to do this using a parametric description. So we're going to have to convert this explicit one to parametric. So first of all, here's what the picture looks like. Hopefully you can see that's an upside down paraboloid kind of shifted up 1 unit. One thing you might want to take note of, if you look in the floor here, what you have is a disk of radius 1, and you can see the paraboloid goes all the way up to 1. So it's kind of similar to what we had here. If you look in the floor, the region in the floor is a disk of radius 1, and the height of our surface goes up to 1. It's just that it's a kind of, this is a hemisphere, right? And this is a paraboloid. So you might be curious or wonder, like, which ones, I mean, we got a positive flux here of 2 pi. You can probably guess that, you know, the flux here is going to be positive too. I'm sorry, it's going to be positive as well, because the normal direction is still defined to be, you know, in the upward, outward direction. But you might wonder, like, which one's bigger, which one is going to give you a larger flux value. And I'll let you think about that just for a minute. Remember, flux is telling you how much of the vector field agrees with the normal direction of the surface. So I'll let you think about which one do you think is going to yield a higher flux. We already got 2 pi for this one and this one. So which one do you think is going to give you a greater flux there? And the answer is this one, because the normal vector for our hemisphere is completely aligned with the vector field everywhere on the surface. So that's maximum agreement. All of F is completely agreeing with the normal direction at every point on the surface. So, you know, theta equals 0 basically everywhere on this thing. So we're going to get maximal agreement. We're going to maximize the flux. But on this one, there's definitely a lot of agreement, but like the normal vector, you know, at different points, the angle is going to be just slightly off, right? So I'm expecting a value not as high as 2 pi, but it's definitely going to be positive. All right, so let's do it. So we need to parameterize the surface. This is not exactly one of the surfaces we did. We did do a paraboloid, but the surface that we parametrized had its vertex at the origin opening upward. So this one's kind of upside down and shifted up 1 unit. So you'll have to kind of think about how you're going to parameterize that. I'll let you guys think about why this actually works. You'll notice I switched the v squared with 1 minus v squared. I would take some time to think about why that works. Yeah, take some time to think about why that works. All right. And then you're going to want to find, let's see, TU cross TV. You can't use TU cross TV for the paraboloid with vertex at the origin because it's not the same surface. So you're going to actually have to do some math here. But assuming you went through the calculations, you would find that TU cross TV equals that vector, which is normal to the surface. By the way, let's see, we've chosen the upward direction to be the flux. So you want to ask yourself if this points in the upward direction. And since, let's see, v is between 0 and 1, the z component is going to be negative. This points in the wrong direction, right? It actually points kind of inward, downward. So it's a real quick and easy fix, though. All we got to do is negate the vector and just use that instead. Okay, so instead of TU cross TV, we'll use a negative TU cross TV there. Okay, all right. So you just plug everything in, plug in your F, your vector field F. Now your vector field F is X, Y, Z. Where is it? X, Y, Z. So you got to replace the X, Y, and Z with your X, Y, and Z on your surface. So you get your entire integral in terms of U and V. So there's your vector field on the surface. There's your there's the negative of TU cross TV, and you're going to take the dot product, and surprisingly, stuff kind of simplifies out pretty nicely, and you'll get V cubed plus V, and the rest is a very simple double integral over the region. By the way, our region here is a rectangle. from 0 to 2 pi in the u direction, 0 to 1 in the v direction. So that's the region R. So there's your limits up there on the left. Okay, and when you run through it, you'll get 3 pi over 2, which is definitely a little bit less than 2 pi, right? It's 3/4 of 2 pi, right? All right, and then let's see. Yeah, we already answered that question. So I think that concludes this section. So I hope that helps.